Well, thank you and welcome everybody to our 23rd Inspiration Exchange session. And the topic for today will be data-centric AI, a new emerging area within our field. So as a very brief overview of today's session before going any further, it's going to begin with Professor Mihaela van der Schaar giving a brief introduction and motivation for data-centric AI. I'm then going to present briefly an overview piece of work from our group and a new tooling method. I'll then turn over to Nabeel Seedat, a PhD student from our group, to speak about a specific new method developed for data-centric AI. We're then delighted to welcome Professor Isabelle Guyon from Google Brain, who will join us for a panel discussion chaired by Mihaela to discuss the latest and greatest in data-centric AI and the vision for the field going forwards. Throughout the session, if you have any questions for any of the speakers or including Isabelle, please do post these in our Inspiration Exchange channel on Slack, and we'll try and take as many questions as possible towards the end of the session for any of our speakers. So we'll post this link in the Slack chat now in case any of you don't have it. So without any further ado, I'd like to turn over to Mihaela for an introduction and motivation for data-centric AI.
It is really a great pleasure, and also I'm very excited to be talking today about data-centric machine learning, which is, like Fergus said, an important new area and field in machine learning that enables robust and reliable machine learning in healthcare, but also many other high-stake applications. Machine learning for healthcare is very diverse, and in these inspiration exchanges, we have talked about a variety of analytics that are built using machine learning, from AutoML to causal deep learning. We also have talked about machine learning interpretability and coming up with discoveries from data. However, there are many issues to be considered in order to successfully develop robust and reliable machine learning systems. And some of these are often overlooked. And what we are going to try to do today is to change this by providing a data-centric lens using machine learning. So what does this mean? The current paradigm in machine learning is model-centric AI or machine learning, where the data is considered somewhat external to the machine learning process. The focus is on model improvement, whether it is developing new architectures, novel loss functions, and optimizing the entire process, like we discussed last time during the Autoprognosis 2 session. Of course, this agenda is important, but we need more reliable machine learning systems in general, and in healthcare in particular, this is of tremendous importance. And the current focus on models and architecture as a panacea of machine learning community often overlooks the fact that machine learning is brittle in complex real-world applications, such as healthcare. So what we believe is that improving the quality and accessibility of data, which is again often undervalued solely as an operational issue, can provide and can empower more reliable machine learning systems in healthcare and beyond. To understand this, let me focus on a few challenges. First, we know that the performance and robustness of machine learning system heavily depends on the characteristics and quality of data. In particular, a variety of data imperfections or limitations are often leading to suboptimal performance and even wrong performance for these machine learning models. Challenges that I have in mind here range from poor quality data to biased data to missing data. And what we really would like ideally is to have a systematic data curation, which is crucial to enable machine learning reliability. However, this is hard. And what we are going to propose today is how we can use machine learning itself to enable such a systematic data curation. But we do not want to stop here. We do not want just to look at data curation using machine learning. In fact, before deploying trained machine learning models, they need to be rigorously tested. And the current de facto standard in learning is benchmark style, where the model is often evaluated on a held-out test set and assessed on average or aggregated performance. And the question is, can we really do better and provide a higher level of rigor for machine learning testing? And what we would like to encourage the community is to consider the role of data, which is crucial in informing model training, but also rigorous model testing, which is needed before deployment. And what we have more specifically in mind here could be, for instance, questions such as, is the current way in which the data set is split between training and validation the right way of doing it? Has the model been evaluated using the correct metrics and stress tests? And many more such questions. Also, we can only realize the value of these predictive models once they are deployed truly in the wild. And this invokes additional considerations to ensure reliability. For instance, we may wish that the models provide reliable predictions when operated under a variety of conditions. We also like to know what the model does know and what it does not know. And this is especially important when we train the model in one environment and test it in another environment. Or like in the time of COVID, the disease is progressing, and hence we need to deal with these drifts in the data and in the disease. So hence, ideally, we would like to have models that are monitored correctly, and given the data and distribution shifts, they are adapted. So we would like to include monitoring and observability to data and distribution shifts as an additional means to ensure system reliability. So in data-centric AI, we seek to give data center stage. And this data-centric AI views model or algorithm refinement as less important, and instead seeks to systematically improve the data used by the machine learning systems. But in our group, we would like to propose a broader definition and go further and call for an expanding definition of this data-centric AI and machine learning, such that a data-centric lens is applicable to the entire end-to-end pipeline in machine learning. So what we would like to propose as a new definition is to define data-centric AI and machine learning to encompass methods and tools to systematically characterize, evaluate, and generate the underlying data used to train and evaluate models. And this means that the machine learning pipeline at the machine learning pipeline level, the considerations at each stage should be informed in a data-driven way. So we propose to apply a data-centric lens. So while we do keep a sharp focus on the data, rather than ignoring the machine learning model, we leverage these data-centric insights as feedback to systematically improve the machine learning model. So we propose this data-centric lens across all the pipelines. For instance, in terms of data, we propose to include considerations that improve the quality of data used for model training, such as proactive data selection, data curation, and data cleaning, as well as synthetic data. And actually, in previous session in Inspiration Exchange, we talked, for instance, about imputation methods such as hyperimpute. Today, Nabeel is going to talk about data suite. And we have also talked in the past about synthetic data, especially in the case of fair synthetic data using VCAF. We also want to use the data-centric lens for training, where we have considerations based on understanding the data to improve model training, such as data-informed model design, domain adaptation, and robust training. Testing, which includes considerations around novel data data-centric methods to test machine learning model, such as, for instance, informed data splits, targeted metrics, stress tests and evaluation subgroups. And last but not least, the deployment stage, which can include understanding and addressing data shifts and drifts, as well as methods to enable trustworthy predictions. And for instance, some time ago, we talked about transductive dropout as a solution to understanding and addressing data set shifts and drifts. And today, Nabeel is going to talk about data IQ as an important lens in enabling trustworthy predictions. But all of this sounds wonderful, yet we do not have a very clear framework to take these data-centric considerations to all the stages of the pipeline. So we developed a tool, a framework that we would like to propose to you, the machine learning community, to take these considerations to data. So I'd like now to give the floor to Fergus to talk about this framework.
So before talking in more detail about this framework, I just want to recap very briefly this notion of data-centric and model-centric, and begin by saying that a lot of the current progress in machine learning so far, which I think we can all agree has been massive, has been around this model-centric consideration, where the data was somewhat treated as a fixed asset, and model iteration was really the focus here, with new models and architectures being developed, better ways of training these models via loss functions, and different optimizers being proposed. However, I think now we're entering this data-centric ML phase, and we're very excited about this, which has been proposed so far, at least, to view this kind of the model stage as a little bit more solved, and really place much more focus on data iteration around things like data acquisition, cleaning, auditing, and even generation. As Mihaela mentioned, I think within our group, we really want to push this area forward by paying attention not only to just the data or just the model, but really by marrying the two together, which is where we see the greatest potential benefit. And we've recently put together a lot of our thoughts with our tool DC Check, which is a data-centric checklist to guide the development of end-to-end machine learning pipelines. Before I explain a little further what this is, I want to discuss other documentation tools in machine learning and really highlight why these can be important. And the first is data sheets for data sets, which is a checklist for data set curation or benchmark documentation, and also model cards for model reporting, which is a checklist for model development. And these have both been very popular in the machine learning community, but also very useful by forcing and encouraging users to really engage with what they're doing and very clearly communicate to the users of both data sets and models how they have been produced, and so on and so forth. However, both of these existing tools are limited to either just the data curation step or the model kind of training and testing step. And we've been inspired by these works and proposed DC Check as a larger, more unifying framework across these to enable data-centric considerations across the entire ML pipeline. So as Mihaela briefly walked through, this pipeline not only consists of data, which is the most obvious area for data-centric AI, but also model training. How does this data actually impact how you want to train your model? Also testing. Only by understanding our data very well can we actually understand how we should test our model. And finally, deployment. We need to continually understand both not only what data the model was trained on, but what data it's seeing after it's been deployed to ensure that the deployment is safe and robust. For the rest of this talk, I want to dive into each of these areas in a little bit more detail, beginning with data. So this encapsulates several topics, beginning with actually how do we come up and select and curate our data? Which data points might we want to collect next in order to make sure our data set is best represented? Where does our data have, where are there missing areas in the training data that we've already collected? Next is pre-processing and cleaning. At the moment, there's a lot of time in industry and in real-world applications of project spent on manually cleaning our data, removing outliers, transforming the data into a form that's more applicable for machine learning methods. And while this is great and very necessary for machine learning to function effectively, we think there's a lot of opportunities here for more automated and informed solutions for doing this. Similarly, data quality evaluation. Not all data points are equally useful, and we need to have a better understanding of which of our data is high quality versus lower quality. And finally, are there areas of our training set that might, or the data we've collected, that might be lacking, that we might need to not be able to collect more, but perhaps generate new data to augment the data that we've been able to collect? Moving on to training, which might seem like almost a paradoxical thing to say in a data-centric AI era, but we really feel that data should inform how models are developed and designed and curated. And this can be in terms of which model selected, or how you can incorporate some data-driven inductive biases into the model development process. But we also need to think from a data perspective about where we're going to end up wanting to use our model. What is the domain of applicability we're interested in? And can our training data assess that? Or perhaps do we need to adapt to our proposed deployment scenario? Or indeed, when we're training our model, what is the actual goal of the model? Do we want a model that is fair and robust to potential changes in data, or do we want something else in our goal? And we think this is very important to keep in mind. And finally, it might be the case that the previous step where I was speaking about data, we're actually unable to remove all of the noise from our data. And so we might need specific methods to train models that are better equipped to deal with noisy input data. Next is testing. I think it's very easy to come up with testing methods that don't fully rigorously, robustly test your model and can therefore overestimate the performance that your model might actually achieve in practice. I think the first of these that we've seen a lot of work in various fields done manually is how we should actually split our data into maybe train test splits, or which data is best to keep out for evaluation. And this might be, for example, if you randomly split, you might not capture data from a certain subgroup that is relatively rare in your data, and therefore you don't actually know how your model will do on that type of data. Secondly, often generalization is key and data in deployment will change. But maybe we want to assess this while testing our model before deployment. And thus we need things like model behavioral testing, or potentially even synthetic data stress testing to allow us to hypothesize about how our model might perform or adjust to data that's beyond the scope of anything we've seen before. And finally, we need to figure out ways of testing beyond just average performance across our entire testing set, so we can really understand where our model shines and when it doesn't. And this can only be done by understanding the different, the nature of the data at hand. And finally with deployment, the model lifecycle doesn't end after you've trained a model and tested it on your internal held out data set and achieved state-of-the-art performance. In the real world, models need to be deployed before they can even begin to be useful. And the first step, obviously, is we need to continue to monitor both our model and the data that's coming in to see, has it changed, has it shifted? And we need to be able to understand and address dataset shifts and drifts. And this can help us inform when we might need to retrain our model or update our data sets in order to improve how the model is going to perform in the current reality of the real world. And finally, we need to be able to trust our model. And this can be things, for example, uncertainty estimation, where we can use our training data to try and get an estimate for a new data point of how certain the model is. But our model should also be able to account for out of distribution data where perhaps it shouldn't issue a prediction and should alert the user that this is something beyond the scope of what it's seen before and can handle. So we bring all of this together within DC Check and provide a series of questions and a checklist for users to engage with in order to force considerations at all stages of these pipelines and help to develop more robust end-to-end machine learning systems. If you'd like to find out more and engage with DC Check, we've got a dedicated website set up with resources at this link.
Okay, so hi, good afternoon, everyone. So my name is Nabeel Seedat. As Fergus mentioned, I'll be presenting Data IQ, which is a recent work where we've looked at characterizing heterogeneous subgroups in tabular data. We've recently presented this at NeurIPS 2022, and this was joint work with Jonathan Krabbe, Ivana Bika, and Mihaela Vandesha. So as reiterated by Fergus and Mihaela, data-centric AI really looks at this idea of characterizing, evaluating, and generating the underlying data used to train and evaluate machine learning models. So the paper that I'll be presenting, Data IQ, really tackles this area of can we actually characterize the data in order to construct higher quality data sets. Before diving in, I just want to briefly highlight another paper which we presented at ICML called Data Suite, which more focuses on the deployment side of can we actually evaluate data at deployment time in order to understand when we should trust predictive models based on the data itself. And for that, there we take a conformal prediction lens on it of uncertainty estimation and actually modeling uncertainty in the data itself rather than the model. And if you are interested in this, I'd encourage you to take a look at the paper or any of the previous inspiration exchanges where this paper was presented. But now jumping into Data IQ. So in this paper, we believe, of course, that data quality matters to any machine learning model's performance. And more specifically, we believe that performance on individual subgroups matters both in medicine, but across all aspects of machine learning deployment. However, in the literature, models are often optimized for average performance because we train with empirical risk minimization. And in this paper, we ask, how can we actually assess underperforming subgroups where we might have heterogeneous outcomes with the goal of better understanding the data and then ultimately constructing higher quality training sets? So in Data IQ, we take a pipeline approach to this, where Data IQ systematically characterizes our training data into subgroups. And we do this using any machine learning model, which we can train iteratively. So these could be stages where you can think of epochs or iterations, and any model that can be checkpointed. So for example, one could use a neural network, but very much so on tabular data where boosting is king, we still believe that XGBoost and light GBMs can be used within this framework because of the iterative and checkpointed nature of these models. We then take these checkpoints theta 1 to theta e, and then at training time, we leverage these checkpoints and we analyze the training behavior of individual examples within a data set, which we call per example training dynamics. And on the basis of these training dynamics, we then characterize each example based on the aleatoric or the inherent data uncertainty, which diverges from more model-centric approaches, as well as looking at the actual prediction confidence. And on the basis of producing these characteristic curves, which you can see to the right of the diagram, we can then stratify data sets into easy examples, ambiguous examples, and hard examples, which I'll dive into next. So how do we actually move now from a training dynamic, which I show on the screen here? So this is green being easy, orange being ambiguous, and red being hard. How do we actually move from this to actually characterizing our data and producing a characteristic curve? As I mentioned, on the x-axis, for each individual sample in the dataset, we can quantify the inherent data uncertainty, as well as the predictive confidence through training. And we say that examples with low data uncertainty and models having high confidence are easy examples for models to actually learn. Those examples where the data is inherently ambiguous, as well as the model itself being uncertain, we can classify in the ambiguous subgroup. And then those examples where, despite the fact that we have low data uncertainty, we actually have low model confidence, we consider these as hard examples. And now that we actually have these easy, ambiguous, and hard examples, one might then ask, like, what would I actually do with this, and how can I make them practically useful? So in Data IQ, we look at 4 pillars, and I encourage you to look at the paper for a more in-depth dive into all of these, but I'll briefly highlight them here. The first being robust data characterization, where we show that the aleatoric or data uncertainty that we model actually provides consistent sample characterization across similar performing machine learning models. Additionally, we show aspects of principal data collection. We show how these subgroups can provide utility both when you want to actively engage with your dataset and do feature acquisition, but also in a static sense when you might want to select between multiple datasets which might have been generated. We additionally look at reliable model deployment, and we show how the subgroups themselves can help guide sculpting of a dataset to ensure more reliable models which generalize rather than simply using the entire training set as is the status quo. And finally, plug and play, where we say that Data-IQ is actually usable with any model trained iteratively, from neural nets to XGBoost, which really give practitioners the flexibility of their choice of model to use depending on their data modality. We first then show some insights on tabular data, of course, in medical settings, these being highly prevalent. So we take a task of prostate cancer mortality prediction, and we see that the easy, ambiguous, and hard groups really represent prototypes within our dataset. And very specifically, the ambiguous group are those patients who have similar features but different outcomes, for whom which we actually need to collect more features with or collect more patient covariates, such as doing more diagnostic tests, in order to actually differentiate them, in contrast to the hard group, which are those patients who actually have this heterogeneous outcome that we're interested in and actually would want to highlight to an actual clinician. But going beyond tabular data, we show that Data-IQ is very much usable even on image datasets. In the widely used Celeb-A dataset, we characterize that actual dataset in order to really understand what machine learning models are doing and how the data actually impacts them. For example, the easy groups show examples where these are examples that models particularly find easy to memorize, where the ambiguous samples actually are those which are inherently blurry or might be obscured or have weird objects placed and actually represent the actual ambiguity in the image itself, with hard examples being those with like incorrect ground truth labels or mislabeling. And this can really help people to better understand their datasets, and on the basis of this understanding, really construct more higher quality training datasets by really auditing using such a method. We extended also, for example, to text data. For example, imagine we were to do sentiment classification for movie reviews. We see that easy examples correspond to examples models are finding pretty easy to characterize as negative or positive and are quite intuitive as well, I guess, to a human being. But the ambiguous examples actually represent, despite the fact of having a negative label, we see in green, part of the review is actually mostly positive and then partially quite negative, and actually represents this linguistic ambiguity that we actually see in the data. And this is a quantitative way to surface something like this. And finally, similar to images, we see that the hard examples are those which do represent mislabeling in the dataset, and hence can show that across modalities from tabular to image to text, the Data-IQ provides a way for practitioners to really audit their datasets, and as a way to then, on the basis of these subgroups, to really sculpt their datasets to ensure that performance is actually better, and we can remove some of these samples we might not even want to in the first place. So finally, the contributions of Data-IQ is that we showed we can characterize samples into subgroups, highlighting the benefit of understanding the inherent uncertainty on the data itself. We provide a useful tool for practitioners to understand quality of data, guiding feature acquisition, and even helping them to sculpt the dataset. And we show utility beyond tabular data. We hope that you'll reach out and engage with our data-centric agenda across all of these works that have been mentioned throughout the session today. Thank you.
I'm delighted now to begin our panel discussion and welcome today's guest, who is Professor Isabelle Guyon, who is a director and research scientist at Google Brain, and is also the chaired professor of artificial intelligence and a researcher at INRIA at the University Paris-Saclay. Today's discussion will be chaired by Mihaela, and we're delighted to welcome you, Isabelle. So Mihaela, shall I pass over to you now?
Yes, thank you very much. And a very big thanks to Isabelle for making time out of her busy schedule to be with us and for inspiring us in her absolutely incredible NeoRIPS plenary talk to think about these data-centric views. If anyone among you has not seen that plenary, you should go take a look. So Isabelle, I want to start with a question. What do you think are the biggest challenges in machine learning that a data-centric lens can help address?
Well, thank you very much, Mihaela, for your kind introduction. I think there's enormous work that's been done now in all sorts of directions by the community of data-centric AI, and it's hard to say, which one is the most important. I think at the moment we should work in parallel, like you highlighted, on all fronts. And not necessarily leave aside one particular aspect, because it's the global, effort that is important. The important important thing is not to leave, any gap. Essentially, in a data analysis effort or in a, machine learning effort in general, the strength of the overall system is not stronger than the weakest link. You can think of it, as a big chain. If there is one of the links that is missing, then essentially everything falls apart.
Thank you so much. So maybe continuing from this question, benchmarks have been key to the development of machine learning models, and you personally played a very important role in creating the benchmark and datasets track at NeoRIPS. Do you think that these data-centric benchmark tasks will be important? And how will they look like? Can you inspire us, the machine learning community, on how to think about these data-centric benchmarks?
So I think it's kind of redundant, right? Data-centric and benchmark, but you're right to point out
I think
that
some people
in fact,
are thinking, yeah, mainly, excuse me, I realize the question is a bit ambiguous. What I meant is quite a lot of current benchmarks have been more on the model side and come up with
yes,
models
you're perfectly right. In fact, it's symmetric in many ways, and current benchmark platforms, like the one we've been putting together that is called CodaBench, respects this symmetry. You can create a benchmark consisting of a number of models that are reference models or baseline models, against which you submit tasks to really hard test them. I think these are going to become more and more important as you see, for example, large language models that are appearing right now and that people are putting to a pretty hard test, but in a not so organized way. I mean, it plays a very important role, to have the entire community poke around, and try to find weaknesses by doing all these very creative testing. But on the other hand, it's hard to come up with some quantitative results in this way. So there is room for devising benchmarks that would be the community submitting tasks to try to corner existing models and use them in ways in which they have not been intended to be used. And this is, I think, actually pretty big departure from previous ways in which we were thinking of benchmarks. In the, I would say, early days of machine learning, people made this big progress compared to, classical statistics to split data into a training set and a test set. But this was pretty much, still in the IID setting framework. And over time, people realized that distribution shifts had a very great importance, and that basically it never happens that when you deploy a system in the real world that the distribution will be strictly identical to that used during the development phase. So that people have at the moment assimilated pretty well in the machine learning community. What is new in the past few months, I would say, or in the past year, is that not only there's going to be distribution shift for the task for which the model was developed, but there will be a change in use of the the models or the systems that are made available. and non-anticipated users will appear. And so this is more than, a simple distribution shift. You could think of it, as the change, of course, in task. If you think of transfer learning or meta learning and the possibility of having multitask learning, this is kind of already encompassed. But it's a bigger change in the sense that even, in the meta learning or transfer learning community, we were always thinking that there exists somehow a meta distribution somewhere that we know already when we start developing the system, how it could possibly be deployed and used, right? For example, it was trained on a number of hospitals, and then it will be deployed in a different hospital, but it'll be still, something about biomarker discovery, and we knew already the task, we never envisioned that a system that was developed for a particular purpose, like, for example, in language modeling, a system that was developed to do question answering for a chatbot, interacting in natural language processing, that this would end up being used to predict Python code. So that's what's happening right now. A model that's been trained to talk with people in natural language ends up being used, in for formal languages like, Python code. So it's a pretty bigger departure, and we have to think about, in the various domains of application that we are thinking of, including medical applications, how will this, change the way in which we think we design benchmarks? Are we going to leave room for, non-anticipated use cases? Are we going to leave room for contribution, crowdsourced contribution from, external people, or contributions from external people that are not necessarily from the entire, population, but from people who are experts in the art? Still, they're trying to think out of the box. How could we use this system in completely different ways, with the risks that this poses, as well as, the opportunities? So this is, to answer your question, this is how we reverse the idea of challenge, right? We start with trained models, and we submit tasks. And of course, there is the more conventional way in which we have a number of tasks, like, in a regular machine learning challenge, and we let the participants submit models to address these tasks.
That's really very inspiring that you are thinking in this way. And I think especially in healthcare, this could play a tremendous difference. Inspired by your question, I wanted to ask you, it's kind of your answer made me think of different types of data-centric AI lenses: meta-learning, causality, uncertainty. Do you think that some of these fields that exist in machine learning would play a more important, a more promising role to enable what you just talked about?
There is a need for unifying these different disciplines and having people talk more to each other, to unify vocabulary, to make sure that we understand what the problems are and how they are being addressed by the various communities. A very, very big challenge at the moment is that when you drop, in a workshop of a different community, it takes you incredible mental energy to understand what people are talking about, because they are using different vocabulary. And the vocabulary is evolving extremely rapidly. So you could be completely at a loss, in a talk, when in fact the concept might not be very difficult to understand, but just because you don't understand the vocabulary. So I don't know how, as a community, we can address that. Maybe we should start having shared lexica. and
or use
and
GPT to translate, to harmonize and standardize language.
Yes, but the problem is that things are evolving rapidly, so I don't know whether, the such models will follow fast enough and adapt to changes in vocabulary. Then the other thing that is important is to separate the problem from the solution. Very often, when people present their work, there is an entanglement between the problem and the solution. So it's not very clear what problem is being addressed, the solution being put forward first. So I believe that, all of these techniques that be them, causality, explainability, I would, include maybe maybe we should think also of even reasoning, in terms of the old AI deductive methods. All these methods, they address some problems, and we need to be clear about what problems they are. So as a community, progress towards maybe categorizing the different types of problems, giving them names. I'm often surprised that there are some family of problems that haven't been identified by names, so it's very hard for people to even understand that they are addressing this particular type of problem. One example that arose recently in our work is that we were working on meta learning and various ways of learning to learn, including reinforcement learning, and we discovered that decision processes that can be modeled as MDP can be categorized in some subfamilies. That some families that are very, very much used include bandit problems, and then there's the slightly more complex family of contextual bandits, and then after that there is nothing else in the hierarchy. You jump, to the most complicated, full, Markov decision processes, where in fact there is, a finer grained hierarchy of type of problems. And I think that would help the community to understand this granularity in order to distinguish what ingredients need to be put into the modeling to address those. So perhaps to tie that with data-centric AI, we have not only data that are already collected from real systems, but data that can be generated with data generative models, for which we control all the assumptions about how data are generated. And if we can categorize the families, of difficulties of problems using artificially generated data, then we can understand better also how to address these difficulties from the model side.
Isabelle, I cannot agree with you more. This is exactly something that we have tried both in the medical world, where often different, seemingly sounding different medical challenges are actually, if you think about them and you formally define them, the same, all the way to trying to create more recently a map of causality, partially to try to understand where we are and where are similar problems, similar assumptions, and similar solutions. So I'm very happy that you see this also in this way, and I think it's very important for the community to really be very clear about problem formalism. And I'm happy you are advocating this. I think it's important in medicine as well as in machine learning. Maybe a final question.
And perhaps, I'm sorry to just complete this in terms of, you asked, the way forward for the data-centric community, and I didn't really address this question. But now, it occurs to me that one thing that is really missing is this categorization of problems. Still, too many people are working only on classification and regression problems. There is
not agree more.
There's no sense of the diversity, of problems that that can and should be addressed. Of course, people now have a sense of what is a recommendation problem, what is a segmentation problem, but it's still, fairly confined to a small number of problems. And the part of the difficulty is that when you go to the real world, often you have an entire chain, an end-to-end, pipeline that you need to address, and that pipeline includes many sub-problems. So there's basically a big jump between the toy problems, like that are reduced to just maybe classification only, and the very complex end-to-end pipelines. We need probably to break things up into identifiable sub-problems that people can tackle, and also, think about how to do the end-to-end optimization. But the sub-problems are conceptually interesting. It doesn't make sense, that people work only on the classification and then nothing is ever, progressing on all the other parts.
Yeah, no, completely agreed. And I think that requires the community to really understand the more complex world we live in, to understand these problems. And like you rightly say, mathematically formalize the entire problem, as well as divide it carefully into sub-problems that make sense. We try to do exactly that. We are obliged, I would say, maybe as a machine learning community for healthcare, and Inspiration Exchange is formed of machine learners in healthcare, we were obliged to be maybe ahead of the curve from that point of view, because in medicine, often to address a medical problem, you need to consider different components. And just to mention something, the features don't come from the sky. They are results of medical tests. So even the way in which data is collected is measured, the cost associated with that. And then how do you continue to monitor somebody after you identify a particular diagnosis? So it's wonderful to see that you think that this is more generally applicable, and I completely agree. I think
yes, I liked a lot, your holistic view that you presented in the previous, talks about data-centric AI. It's very critical to have a holistic view.
I maybe have a final question, and because I'm sure the audience has many questions as well. And this is maybe a seemingly simpler question, but I think it's still a challenging one. What properties do you think high quality, good data possess? What makes good data good?
What makes good data good? It depends a little bit on the context. Good for what? So we highlighted the need, and I highlighted that also in my talk. I guess I got that initially from the social science people, including Timnit Gebru, that data has to be for a purpose. And that maybe escaped many people who were just collecting data. Let's collect data and we'll see afterwards what we'll do with the data. If you don't collect data for a purpose, it's very likely that it's not going to be good for any purpose. So there's some planning that needs to be done when you prepare a data set, and that planning includes many components, and in particular, it includes defining tasks ahead of time. And the tasks, include metrics, include, and that basically defines the purpose. One mistake, I believe, is to do it the other way around. Start collecting data and then think afterwards, what are we going to do with those data? Then it's too late. You're not going to collect the right data for your purpose. And then the second...
Very much the case, sorry to interject, in medicine, that's very much the case, because often you collect data sets, and unless you know how they're going to be used in practice, just these data sets are not going to be sufficient.
Exactly, and of course that includes, then planning for having sufficient data and sufficient metadata to make sure that there will be no unknown confounder that afterwards you will be very sorry about. But this takes, a while, and this takes having on the team that collects data a number of experts that can scrutinize the protocol of data collection for identifying, potential biases, of course, the study population, potential confounding bias, etc. So it is basically a job in itself to know how to collect good data. And you don't learn that at school or from textbooks. You learn that on the job, right? Because you need to have made yourself many mistakes to then, you know, be alerted to what all nightmare cases that can happen.
And more than that, I think to some extent, this data is often expensive to collect and complicated. So one needs to think more holistically and include multiple parties that may have, I guess, stakes in this data.
And one very important thing that you mentioned
for this data.
One of the very important things that you mentioned is that it's an iterative process. You basically need to start collecting small sample data, pass it through your models, check, you know, what's happening, and iterate. And if you just collect a huge amount of data and spend $1 million, you know, and then to do your analysis post hoc, very likely you're going to be very sorry about it, because your models.
Very often the case in medicine.
Yeah. So it's a very good idea, you know, to go step by steps, and that's often what we do. You know, when we design challenges, we do a first trial challenge for a smaller conference, you know, in which we use sample data, we try the entire protocol, we look at the results of different models, and we learn from that, and then only do we, you know, collect the larger data set. And then, of course, you know, it's silly to repeat what everybody is saying, but I don't want, you know, to miss the important point that collecting data comes with responsibility. So good data is, you know, is also data that has been collected responsibly by checking, you know, having proper consent from the subjects, from original data owners, from everybody, right? From the people who are giving you instruments, resources, everything everything that you use to collect your data needs to come with, you know, responsible ways of using it, anticipating wrong ways of in which the data can be used, giving proper credit, etc., etc. So that's very important.
Thank you very much, Isabelle. I know you need to leave, but thank you very much for the time you gave us and all these wonderful insights and food for thought. Thank you very, very much.
Well, I'm, you know, very excited to see that there is this dynamic community of data-centric AI. I see one of my grad students has now joined, and I hope he will stay longer and benefit from the rest of your presentations. And I'm very much looking forward, you know, hearing them offline. I think that you're recording, right?
Yes. Thank you very much.
Okay.
Thank you very much, Isabelle.
Thank you all. Bye now.
Fergus, I'm going to now give the microphone to you.
Great. No, thank you. And that was an amazing discussion with Isabelle. So I hope everybody enjoyed it as much as I did. We're now going to open up for the more general Q&A type session. So there have been some questions posted in our Slack, and we're going to try and take as many as we can in the time we've got remaining. So if I call on you, please can I ask you to unmute and ask your question as succinctly as you can, and then we can direct it towards the best person to answer it. So perhaps if we could start with Ben Wilson. I think you had a question.
Hi, yes, apologies for lack of a camera. My question is relatively short. I've seen on the slides there the idea of proactive data selection and curation being the starting point for the whole process. And the point has actually been emphasized in the discussion about that process is not value neutral. How we approach it depends on our objectives, but it also depends on external constraints that might reflect biases in previous and historic data capture. So it's a very generalized question. How do we constantly review this, and how does that impact the way that everything subsequent to that is obviously impacted? And how do we make sure that everything subsequent is informed by what we find when we continue to review?
Thanks, Ben. Nabeel, would you like to answer this?
Yeah. So thanks for the question, Ben. Like, I actually totally agree with you, especially on this point of it being at least some value related to it. And I think right now the thinking, at least in the work we've done so far, has been how can we use machine learning, yes, to highlight some of these issues in data which might prompt further data collection or more proactive data collection. But I think the key aspect has been still to keep, for example, in a healthcare context, keep a clinician in the loop such that there is this value assigned to it. It's not just machine assigned or through a machine learning model. There is still a human kept in the loop to figure out if changing the data collection process to be more proactive and address some of these issues might actually bring the desired value down the line. So I do think like a human aspect is very much needed, at least in this process, aligned to your question.
If I could add maybe a couple of quick things.
Yeah, apologies, I'm jumping, sorry for that. So another thing that I think it's important, sorry Ferguson, I think you may have yet another point, is this whole idea of active sensing, active monitoring, personalized monitoring, which is very much a strand of literature in machine learning for healthcare, in our own work, but many other people are working in this area, where one could identify the value of information for a particular individual, a cohort, but also potentially for a particular set of tasks. So I think the field of active sensing and active monitoring can contribute. Sorry, Fergus, I got excited about the question.
No, all good, all good. I think the two things I definitely wanted to add to this, I think is, the first is, I think being aware that these things have the potential to not be value neutral is very important. And at the moment, a lot of data curation is, I don't want to say by luck, but just occurs. And I think forcing people to think, like forcing yourself to think about it and engage with it, and actually having machine learning, like maybe new methods and ideas and algorithms that can help you collect data that is consistent with your stated values is definitely a step in the right direction versus just happening to have the data that you happen to have. I think the other point maybe though, to disagree with what you said just a little bit, is that I think some of the maybe preliminary methods that are of most interest right now, I think you could make an argument they are maybe value positive in the sense that perhaps some of your data is just objectively corrupted, or has, let's think in a medical context, there are some medical data sets where accidentally for the image of an X-ray, they left in an annotation on the image that actually said basically what the outcome was. And obviously, depending on whatever your value system is, that is clearly not useful data for a machine learning system. And being able to characterize and identify this more easily to then actually just create an objectively better data set, or perhaps crop out that part of the image or change how your data collection process is going forwards, I think is objectively a good thing. So those are the two things I wanted to add on top of what you said. The next question I'd like to take is from Morteza. I think hopefully I pronounced this correctly. Perhaps you could unmute and ask your question about benchmarks and data sets. Not sure if you're still there, perhaps you had to drop. So I'll just read it out then quickly. Regarding benchmarks, I would like to ask how we can create more challenging data sets to mimic real world data sets. Nabeel, perhaps you want to take this one?
Yeah, I think, at least obviously this is still brainstorming, but in terms of benchmarks that we probably do require is both in terms of what type of data is included in the benchmark data set in the first place, of is it challenging enough such that it reflects what could be the real world scenario that the state-of-the-art model is being benchmarked against. So I think that's probably the first thing, of what is actually included. Do we include even things like where we might see a distribution shift in our benchmark to see how models do react under these stressful scenarios? But I also think within a benchmark data set, we've got this paradigm right now where we evaluate on average on this big data set, and we report one number at the end, and we're like, this number is better than this number, hence this method is better. And I think this notion of, can we test on individual subgroups that we actually start caring about, and then seeing how models differ on performance on these different subgroups, is perhaps also another interesting area to ensure like these benchmarks are actually testing things that we do care about.
Fantastic. Thank you, Nabeel. In the interest of time, I think we're going to have to close off the Q&A session now, but we'll try and answer as many questions that have been posted on Slack as we can after the session has ended. So just to briefly wrap up, we thank obviously everybody who is able to join for today's session. Today's session has been being recorded, and we hope to post this on YouTube very shortly. So if you have any colleagues or friends that missed today's session, please do send this their way. This was our last session for the year before closing off. So I guess happy holidays to everybody. And our next session, which will be the 24th Inspiration Exchange session, will take place on the 1st of February, where the topic will be on synthetic data and generative modeling. If you'd like to stay up to date on Inspiration Exchange, do visit our dedicated page and sign up if you've not done so already. And please let any friends or colleagues know about Inspiration Exchange. Thank you, everybody. And I hope you enjoyed today's session, and we will see you in the new year for our next session on synthetic data.